While in an ordinary transistor, billions of electrons flow to provide a measurable current, in semiconductor quantum information, we are interested in operating and controlling electrons one by one. We do this by fabricating tiny metallic electrodes on a semiconductor material. Typically, a dielectric is placed in between the semiconductor and the metal to electrically isolate the two from each other. By applying electric voltages on the metal, the gate, we can tune the potential landscape underneath to become an island, what we call a quantum dot. Due to the strong quantum confinement, a quantum dot has discrete energy levels and as a result, a countable number of electrons. The potential landscape may be further tuned via additional gates that control the coupling of the quantum dot to the source and the drain. Let's first focus on a quantum dot in isolation, and several energy scales are relevant. To put things in perspective, we compare the energy scales to the thermal energy for a Fermi direct distribution, set by the Boltzmann constant. Room temperature corresponds to a thermal energy close to 30 millielectron-volt. Now, let's compare this energy scale to the energy scales for an electron in a quantum dot. First of all, there's a charging energy that needs to be overcome when an electron is loaded in the island. For sizes of about 1 nanometer, corresponding to the potential profile of donors and acceptors in the semiconductor, the energy scales are an order of magnitude larger than the thermal energy at room temperature. But this energy scale quickly reduces for larger quantum dot sizes. For quantum dots that are lithographically defined, typical sizes are of order 100 nanometers. And then, the charging energy is only about 3 millielectron-volt. Thus, in order to observe the discrete nature of a semiconductor island, we need to cool toward low temperatures. But next to the charging energy, there is also a confinement energy. In an isolated quantum dot, the electron wave function vanishes outside the quantum dot region. And this boundary condition leads to discrete energy levels. For a quantum dot of size 100 nanometer, these energy scales are of order 1 millielectron-volt typically. Smaller, but comparable to the charging energy. And thus we need to operate at low temperatures to work with a discrete number of electrons. As a side note, many decoherence processes are also temperature dependent. Thus there are even more reasons to work at low temperature. We therefore put these quantum dot systems in a dilution refrigerator that has a typical base temperature of about 10 millikelvin. And now that we understand the filling of an electron inside a quantum dot, can follow a remarkable filling. If we consider a circular potential landscape, the orbital energies follow a pattern that mimics the pattern of electrons in the real atom. That is, the electron filling follows Hund's rules in 2 dimensions. Here you see a first demonstration of this filling using the material gallium arsenide. For electrons in silicon, however, things work differently. The band structure of silicon is such that electrons experience a degeneracy due to the crystal symmetry. In silicon, there are so-called valley states, and each orbital can be filled with 4 electrons, 2 for the spin and 2 for the valley. Holes in silicon do not experience this degeneracy, and the filling is again as usual. Thus, there is only a spin degeneracy. While these fillings are interesting demonstrations of quantum dots as artificial atoms, details such as valley degeneracy are highly relevant for quantum information. Ideal qubits are represented by isolated qubit states, and valley degeneracy can cause interaction due to the energy states being close to the qubit states. And that is, for electrons in silicon, the isolation is not determined by the orbital energy, but by the valley energy. Indeed, a great effort in silicon quantum technology is to boost the valley energy. Now that we understand how quantum dots work in isolation, we focus on the electrical transport when a quantum dot is coupled to electric leads. We consider a quantum dot that is tunnel coupled to a source and a drain. Thus, electrons can reside in a quantum dot, but can also reside in reservoirs containing many electrons. Due to the discrete nature of the quantum dot, electric current can only flow from the source to the drain once a quantum dot energy level is aligned in between the source and the drain level. And as a result, upon changing the quantum dot gate voltage, current can flow depending on the alignment of these energy levels. When operating at very low temperatures, at or below 1 or a few Kelvin, current peaks at very sharp positions in voltage space. This means that the current through a single electron transistor is strongly dependent on the electric field. This field may come from the gates to tune the quantum dot. The electric field may also come from electrons in other nearby quantum dots. That is, a single electron transistor is a good sensor for nearby electric charge, and that turns to be very relevant for quantum computation with quantum dots. Now, let's see how measuring a quantum dot works in practice. We first consider a double quantum dot. In the case that there is no capacitive crosstalk, the energy levels corresponding to the electrons in a quantum dot are spaced horizontally and vertically in a so-called stability diagram, where the axes are spanned by the gate voltage. When there is finite crosstalk, which is always the case in real scenarios, the lines start to bend. In addition, there may also be an interdot coupling. The capacitive interaction between the electrons in the two quantum dots results in an anti-crossing in the stability diagram. And we can measure this by applying current through the double quantum dot system. However, only current can flow when both levels are inside the source-drain window. Instead, if we use a nearby charge sensor, we can elegantly measure whenever an electron is added to one of the two quantum dots. Scaling beyond two quantum dots, such as in the 4 quantum dot system as you see here, results in an even more complicated stability diagram. And one of the challenges in scaling quantum dot systems is to tune the quantum dots in a scalable manner. Possible methods that are currently being explored include machine learning to tune in an automated fashion. Indeed, the tuning itself should also be scalable in order to progress to large systems. And this is realized via the tuning method, but also by the quality of the system. A specific goal is to obtain uniformity such that having a single electron in a quantum dot can be achieved by a common gate voltage. If that is feasible, many of the concepts used in classical technology can be adapted to scale quantum dots, such as the word and the bit line addressing used in DRAM cells with crossbar technology.